Hi there everybody, welcome to iTTV. For today's lesson, we will be looking at oxidation and reduction. So the learning outcomes for today's lesson would be, by the end of the topic, students should have a better understanding about the differences between electrolytic and voltaic cells, and we'll move on to corrosion of metals as well as methods to prevent corrosion of metals at a high rate. So let's first look at transferring of electrons at a distance. If you refer to the slide, transferring of electrons at a distance occurs between two electrodes in two different electrolytes. Like the voltaic cell, the electrons flow from the negative electrode to the positive electrode. So there is a picture of a U-tube whereby in one tube they put in potassium iodide solution, whereas on the other arm of the tube there is bromine solution. And in between, there is dilute sulfuric acid that has to be an electrolyte. For this particular setup, the negative terminal is actually the terminal that contains the potassium iodide solution. So iodine ions will become oxidized to brown iodine solution. So the change in color will be from colorless to brown in the potassium iodide solution. Whereas for the positive terminal that contains the bromine solution, bromine is reduced to bromide ions that are colorless. So this was a simple setup of to show how electrons can be transferred at a distance, and the setup is very similar to a voltaic cell. So what are the observations for the setup as shown? That for the potassium iodide solution, which was originally colorless, it becomes brown in color. Whereas for the bromine solution, it changes from brown to colorless. So the overall equation would be two iodine ions reacts with bromine molecule to produce iodine molecules as well as two bromide ions. And the substance oxidized in this case is iodide ions, while the substance reduced would be bromine molecule. Oxidizing agent is bromine molecule and reducing agent is iodide ion. The function of sulfuric acid is to allow ions to pass through. So with this setup, we are able to deduce which is the oxidizing agent because it would be the substance that is reduced. And in this case here, bromine is reduced to colorless bromide ions. Therefore, bromine is the oxidizing agent. While for the reducing agent, it would always be the substance being oxidized, and in this case will be colorless iodide ions that will be oxidized to become brown iodine solution. So in this case here, the reducing agent is iodide ions. The reason why the U-tube was added with sulfuric acid between the iodide solution and bromine solution is to allow the ions to pass through freely between the two solutions. So let's look at another example, where in one tube, iron 2 sulfate solution was added, whereas in the other arm, acidified potassium manganate 7 solution was added. And the dilute sulfuric acid was also added to separate the two solutions and to allow the flow of ions to pass through. For the oxidation half equation, iron 2 plus becomes oxidized to iron 3 plus. Therefore, the observation expected would be from light green to brown color solution. And the reduction half equation that happens on the other arm of the U-tube will be the permanganate ion is reduced to become colorless manganese ion. So the expected observations would be in the arm that contains iron 2 sulfate solution, it changes color from light green to brown because Fe3+ is brown in color. And in the other arm, which contains the potassium manganate 7 solution, it changes color from purple to colorless. And the overall equation would be that 5 moles of iron 2 plus ions reacts with permanganate ions, as well as 8 protons to produce 5 moles of iron 3 plus manganese ion, and we also get 4 moles of water. The substance oxidized in this case would be iron 2 plus, while the substance reduced will be the permanganate ion. Oxidizing agent is the permanganate ion, and reducing agent will be iron 2 plus. So for this other interesting example, to illustrate transfer of electrons at a distance, we use iron 2 plus, whereby it will be easily oxidized to iron 3 plus. So there is a change of color from green to brown. A way for students to easily remember this is that if, let's say, you have a green apple and you leave it outside in the air, when it oxidizes, it becomes brown. So it's easy to remember that from iron 2 to iron 3, it changes color from light green to brown. In the other arm of the U-tube, the permanganate solution that is very purple was added in. And permanganate solution is a very good oxidizing agent, so naturally it will be reduced to colorless manganese ion. So again, oxidizing agent is always a substance that is reduced, and in this case is the permanganate ion. And a reducing agent is always a substance that is oxidized, and for this setup will be iron 2 plus ion. So let's move on to a simple concept that students need to remember, that oxidation occurs at the anode and reduction occurs at the cathode. So if you refer to the simple diagram in the slide, there is a setup of an electrolysis apparatus setup, whereby the electrolyte used will be dilute sodium chloride solution. And the oxidation half equation that happens would be that 4 moles of hydroxide ions will produce 2 moles of water plus oxygen gas as well as 4 electrons. While the reduction half equation that happens would be that 2 moles of protons would react with 2 electrons to give you hydrogen gas. So because H plus is less electropositive than sodium ions, therefore H plus will be selected to be discharged at the cathode, because reduction always happens at the cathode. Whereas in sodium chloride solution, which is dilute, the negative ions that will be present will be chloride ions as well as OH minus ions, and you can see that also in the slide. So which ion will be selected to be discharged would be again the less electronegative ion, which in this case here is OH minus. So OH minus will be selected to be discharged to produce oxygen gas. So with that, let's look at a simple demo on how to further increase your understanding about this electrolysis setup. So this is the electrolysis setup, and the electrolyte is dilute sodium chloride solution. As you can see, the green crocodile clip is attached to the positive terminal of the battery. Positive terminal to this particular carbon electrode. So positive terminal for electrolysis means that this will be the anode. So this electrode here will be the anode, and oxidation is expected to happen in this anode electrode. So therefore, this electrode on my right here is the cathode. The cathode for electrolysis is usually the negative terminal. So if you follow the yellow crocodile clip, it will go to the negative terminal of the battery. So let's on the power switch to show the expected observation that there would be 2 different gases produced at the upturned test tubes here. So let's start the experiment now. So it will take some time for the gases to be collected. But let me do a little bit of explanation. As mentioned earlier, this electrode is the anode. So at the anode, oxidation will happen. What substance is oxidized? As previously mentioned, that hydroxide ions will be selected to be discharged, and hydroxide ions will undergo oxidation to produce oxygen gas here. So we would expect that there will be some gas bubbles that will come out and oxygen gas will be collected here. Now this is the cathode, and it would be expected that at the cathode, hydrogen ions will be reduced, and hydrogen ions, upon reduction, will produce hydrogen gas. So hydrogen gas should be collected over here at the end of the experiment. So in conclusion, this should be oxygen gas and this should be hydrogen gas collected at the end of the experiment. We would have to wait for some time because this experiment takes quite some time to happen. So as you can see that there was a lot of gas bubble formation at the cathode electrode, the electrode on the right hand side, whereby a certain amount of gas has been collected at the top of the test tube. There was also a very tiny amount of bubbles produced at the anode electrode, the electrode on the left. As you can see, a small volume of gas has been collected at the anode. At the anode would be oxygen gas. At the cathode would be the hydrogen gas. So there's a lot of hydrogen gas produced as compared to oxygen gas. So these are what happened at the end of the experiment. That this will be the anode and this will be the cathode electrodes. So oxygen was collected at the anode as mentioned earlier because hydroxide ions were selected to be discharged, and hydroxide ions actually were oxidized to produce oxygen gas, and you saw some gas bubbles being formed at the start of the experiment. So this is the small amount of oxygen collected after the experiment, and this electrode here would be the cathode, whereby reduction has occurred. So there was a lot of gas bubbles formed here because hydrogen ions were selectively discharged to produce hydrogen gas. Hydrogen ions were reduced to produce hydrogen gas that is collected at the end of the test tube. So this was a simple electrolysis of dilute sodium chloride solution. So let's look at a Voltaic cell. Voltaic cells are different from electrolytic cells, but the similarities would be that oxidation occurs at the anode and reduction occurs at the cathode. So if you refer to the Voltaic cell setup in the slide, there are two half cells whereby one beaker is filled with copper 2 sulfate solution and the other half cell is filled with silver nitrate solution. And you have a copper electrode acting as the anode that is immersed in the copper 2 sulfate solution and a silver electrode immersed in the silver nitrate solution. So the oxidation half equation that happens would be that copper releases 2 electrons to produce copper 2 plus. And reduction half equation would be silver ion gains 1 electron to be silver atom. So as you can see, that was a simple Voltaic cell, whereby in this case here, usually the more electropositive element will be the negative terminal, which would be the anode. The similarities between Voltaic and electrolytic cells would be that oxidation always happens at the anode and reduction always happens at the cathode. So the observation for the setup in the slide would be that the intensity of the copper 2 sulfate solution, blue color intensity, will increase with time. And for the silver nitrate solution, it will be observed that there will be this silvery grey crystals being formed, indicative of silver metal. Now Now let's have a look at the differences between electrolytic and voltaic cell. For electrolytic cell, the type of electrode should be the same, while for voltaic cell, the type of electrode is different. Energy change for electrolytic cell is from electrical to chemical, while for voltaic cell, it will be from chemical to electrical. The cathode in electrolytic cell is the negative electrode, while for voltaic cell, it will be the positive electrode. The anode in electrolytic cell is the positive electrode, but for voltaic cell, it is the negative electrode. But for both electrolytic and voltaic cells, the reaction at the anode will be oxidation, while for both electrolytic and voltaic cells, the type of reaction at the cathode would be reduction. So there are certain similarities, and yet there are also differences between the voltaic cell and the electrolytic cell. The most remarked difference between the two types of electrochemical cells will be firstly the energy change, as well as what is the charge of the cathode or the anode. So with that, let us look at corrosion of metals. Corrosion of metals happens in the presence of electrolyte. Oxidation of metals to metal ions occurs spontaneously through the loss of electrons. Example, magnesium loses 2 electrons to become magnesium 2+ ion. So rusting of iron is whereby oxidation of iron happens in the presence of oxygen in the air and water. So rusting of iron is a very good example of metal corrosion. If we look at the diagram in the slide, there is a droplet of water on a piece of iron metal. So if you notice, there are regions A and regions B. Oxygen will actually be reduced by receiving 4 electrons to become 4 OH-. So the oxidation number of oxygen has changed from 0 to -2. And for the piece of iron there, iron will be oxidized in the presence of water to produce iron 2 hydroxide. So iron 2 is produced and it will further oxidize to produce iron 3 oxide, which is hydrated with X molecules of water, and that is the brown iron rust. So to further explain this in detail in words, okay, at B, region B, which is known as the anode, the iron atoms release electrons, whereby iron releases 2 electrons specifically to become iron 2+ ion. And these electrons then flow to A, which is the cathode. At region A, the concentration of oxygen is high, so oxygen reacts with water and gains 4 electrons to produce 4 hydroxide ions in a process known as reduction. So the overall reaction for this rusting process will be 2 iron atoms reacts with 1 molecule of oxygen as well as 2 molecules of water to produce 2 molecules of iron 2 hydroxide. Iron 2 hydroxide is further oxidized to iron 3 hydroxide, which then decomposes to hydrated iron 3 oxide. So as you can see in the equation, 4 moles of iron 2 hydroxide reacts with 2 moles of water and oxygen to give us 4 moles of iron 3 hydroxide, which is further hydrated to give us hydrated iron 3 hydroxide, whereby X is an integer. So iron 3 hydroxide or hydrated iron 3 oxide is the brown coating found on the surface of rusty iron, and the chemical contains iron 3+ ions. So that was a very detailed explanation of the rusting of iron. That is actually a series of chemical reactions, and there is actually a small voltaic cell actually produced at the site of iron rusting, and the rust itself is known as hydrated iron 3 oxide, which contains iron 3+ ions. So this is one of the most popular exam questions with regards to this lesson, so it's important to take note of all the equations and explanations. Now, what about electrochemical corrosion? Oxidation of metals to its metallic ions when it is in contact with a less electropositive metal in the presence of an electrolyte. For example, M will be oxidized to become Mn plus by releasing n number of electrons, and big M here refers to the metal. So that's the definition of an electrochemical corrosion. Now, so let's have a look at a simple setup to illustrate electrochemical corrosion, whereby we have 3 test tubes labeled A, B, C, and all 3 test tubes contain a iron nail. All 3 test tubes are also added with 3 solutions. One is gelatin solution, secondly phenolphthalein solution, and thirdly potassium hexacyanoferrate 3 solution. Now, the test tube B contains iron nail plus copper. It has been covered with copper. And test tube C contains iron nail covered with magnesium ribbon. So, gelatin solution is added, and phenolphthalein is there to test the presence for hydroxide ions, while the hexacyanoferrate 3 solution is to test for the presence of iron 2+ ions present in the test tube. So, let's look at the results of this experiment. If let's say, it has been let on to carry out for some time. So, in test tube A, the intensity of the dark blue was low, indicating that the concentration of 2+ is low. The intensity of the pink color, well, there is none in test tube A. So the inference will be that Fe2+ ion has been formed and iron has been corroded. In test tube B, the dark blue intensity is high, indicative of a high concentration of Fe2+ ions. Intensity of pink is low. This can be inferred that Fe2+ ion is also formed and Fe is corroded. What about test tube C? There is no dark blue solution formed. Intensity of pink is also very high. Inference will be there are no Fe2+ ions formed. Therefore, iron not corroded in test tube C. So if we look at it, in test tubes A and B, both the iron nails were corroded as indicated by the results of the experiment. The intensity of pink color is due to the phenolphthalein and it detects the presence of OH-. If the amount of OH- is very low, it means that rusting process has occurred because hydrated iron 3 oxide is produced. But in test tube C, how come there is no corrosion? There is some properties of the magnesium ribbon coated onto the surface of the iron that prevents corrosion of iron. Let's have a look at the half equations happening in test tubes A and B. In both of these test tubes, iron has been oxidized to produce iron 2+ ion. While in test tube C, magnesium is the one that has been oxidized to produce magnesium 2+ ion. So the conclusion would be that the less electropositive metal will cause iron to corrode faster, whereas a more electropositive metal such as magnesium will prevent the iron from corrosion when in contact with iron. So, if we coat the iron nail with a more electropositive metal than iron, it will prevent and protect the iron nail from corrosion. But if we want to speed up the corrosion of iron, we coat the iron with a less electropositive metal such as copper. So, thereby comes our applications on how to prevent rusting. Firstly, we need to prevent the surface from exposure to water and air. How do we do that? Would be firstly, applying a protective coating, for example, paint or grease or even wax. Secondly, we could have a plastic coating, for example, wire fencing that is green or even clothes hangers. Thirdly, electroplating with a metal low in the electrochemical series, for example, with gold, silver or nickel. So these three methods mentioned are ways to prevent the surface of the ion from having contact with air and water. As long as there is no water, there is no air in contact with iron, this will prevent or even slow down corrosion. Other ways to prevent rusting will be tin plating, for example in food cans, because food cans contain iron. Next, we have galvanizing, which is coating with zinc, for example zinc roofs. So all these are ways to prevent the rusting of iron. Well, the next other major method to prevent rusting of iron is to use a sacrificial metal, which is a more electropositive metal, to form the sacrificial anode. Example, bags of magnesium scraps are attached to underground pipes. Secondly, zinc blocks are attached to the bottom of a ship, as illustrated in the diagram below. So, based on the experiment that we discussed, that using a sacrificial metal, a metal which is more electropositive than iron, for example magnesium or sodium or even zinc, it will be able to prevent rusting, because the more electropositive metal will be corroded first. Third major method to prevent rusting would be alloying. For example, stainless steel is an alloy of iron with nickel and chromium. The metal oxides of nickel and chromium formed on the surface is impervious to water. So alloying is indeed an effective way to prevent iron rusting. So let's look at our first question for the lesson. The diagram shows an experiment to study redox reactions. Which statements are true during the reaction? First, electrode Y is the negative electrode, and 2, the sulfuric acid is the reducing agent. The purple color around electrode Y is changed to colorless. 4, electrons flow from electrode X to Y. So option A, Roman numeral 3 only. Option B, 1 and 3 only. Option C, 3 and 4 only. Option D, 2, 3 and 4 only. Now for Roman numeral 1, electrode Y is the negative electrode. Is it correct? Firstly, remember for this setup, you have iron 2 plus sulfate and you have the potassium manganate solution. Let's jump to the board to have a better understanding for this question. So, we have the presence of Fe2 plus in one arm of the tube, and we have our manganate ion in the other arm of the test tube. So which ion would be easier to be oxidized, as in has a higher ability to give away electrons? That would be surely Fe2 plus. It is so much easier for iron 2 plus to release electrons to become iron 3 plus, and this process is known as oxidation. So for MnO4 minus, it is easier for it to be reduced into Mn2 plus, and we need to balance this equation. So manganese is already balanced. Then we can add 4 molecules of water here, balance with 8 protons, and this will be 5 electrons. The way to balance this will be taught much later. Okay, so for option number 1, electrode Y is the negative electrode. You can notice that because oxidation has happened to iron 2 plus, so iron 2 plus actually will give you the negative electrode. As in the electrode immersed in iron 2 plus solution is the negative electrode. So therefore, to say that electrode Y is the negative electrode is wrong, because the answer will be electrode X is the negative electrode. So electrode X is immersed in iron 2 plus solution, so electrode X is the negative electrode. Therefore, Roman numeral 1 option is wrong. Now part 2, the sulfuric acid is the reducing agent. It obviously is wrong because sulfuric acid is present there to allow the ions to move through. So that is wrong as well. Let's look at option 3. The purple color around electrode Y is changed to colorless. And that is certainly true because this is purple color. This permanganate ion is purple color and it will change to colorless because the manganese ion is colorless. So option 3 is correct. Option 4, electrons flow from electrode X to Y. That is certainly true because iron 2 plus has released electrons which will be accepted by the permanganate ion. So the negative electrode here will be electrode X, while the electrode that is immersed in the permanganate solution is electrode Y. So essentially electron flow is from X all the way to electrode Y. So the answer for question 1 is option 3 and 4, which means the answer is C, 3 and 4. So let's have a short recap for today's lesson. We looked at transferring of electrons in different electrolytes being transferred at a distance using the U-tube. And we looked at rusting as an oxidation process. And further on, we looked at methods to prevent the rusting of iron, especially using a more electropositive metal as the sacrificial metal to prevent rusting. So that's the end of our recap. Okay, thank you so much for watching iTTV. We look forward to see you again the next time. Thank you and have a great day.